Hello. Today, my peers and I will be presenting on solving the SHA-265 cryptographic hash function of Bitcoin. This presentation will do the following: explain what Bitcoin is and how it works, describe the cryptographic hash function, discuss equipment needed to calculate cryptographic hash functions, give instructions on how to calculate cryptographic hash functions, and provide troubleshooting information. So you might be wondering, what is Bitcoin? Bitcoin is a digital currency that was created in 2009 by someone using the alias Satoshi Nakamoto. This currency is decentralized, meaning the government does not regulate it. Purchases made with Bitcoin are made anonymously in the sense that no actual names are used, but rather a unique digital ID. Also, there are no transaction fees associated with Bitcoin. You only pay what the item you want costs. Bitcoin utilizes different encryption techniques designed to regulate currency generation as well as verify transactions. Bitcoins are not printed or created by the government, so they are generated through a process called Bitcoin mining. This involves using computers to solve complex math puzzles that, if correctly solved, rewards 25 Bitcoins to the person responsible for solving the problem. Bitcoins get stored in a digital wallet, on a local computer, or in the cloud. This wallet serves as a virtual bank account that allows users to send and receive Bitcoins, pay for goods, and save their money. All transactions are recorded in a public ledger. That includes their wallet IDs rather than their names. The digital transaction requires many encryption measures, including something called a cryptographic hash.
So after all this talk about Bitcoins and what a Bitcoin is, now we get down to the real meat and potatoes of what the heck cryptographic hash is in the SHA-265 algorithm. So, every time you make a transaction, the transaction must be verified by using the SHA-265 algorithm, which in itself is a cryptographic hash. Now, to understand that, we need to break that down even further. A hash function is any function that can convert an arbitrary number of inputs, meaning just any number of inputs you want from 0 to infinity, and still create a fixed output. The inputs to the hash function are called keys, and the output can be referred to as the hash or hash value. Now, cryptographic hash is just a subset of the hash function, and it's a very specialized case. It's when for any number of inputs, no matter what, you will always get a different output. So, in contrary to addition, if you add 2 plus 2, you get 4, or you can add 1 plus 3 and get 4. With a cryptographic hash, there's only one way to get 4, and no other way is possible to get the same output. So this creates sort of a digital fingerprint, as each output is unique and cannot be solved or repeated again. So this gives a way to verify transactions. And this happens when you get a hash value that has a certain number of zeros in the beginning based upon the agreed upon difficulty at the time, which is set by a proprietary standard. And so when a hash is found that has a certain number of zeros, then the block is considered complete and solved. So why should you solve a cryptographic hash function by hand? Well, there could be a number of useful situations other than just understanding the underlying logic of bitcoins and cryptocurrency. But it could be useful for, let's say, you want to make specialized hardware to solve Bitcoin hash function. It'd be really, really useful to know how that hash function actually works. If you're making software that interacts with the hash function hardware, or you're creating software to pool together a bunch of computers or miners, as they're often known in Bitcoin, to distribute work more effectively. Maybe you want to make an entirely new cryptographic hash function, or you have some unique way to apply cryptograph hashes. So all these are very good reasons for why you should learn how to solve a cryptographic hash function by hand.
The standard procedure for solving the SHA-265 cryptographic hash function requires of a simple white paper, pencil, binary calculator, and a binary conversion table. The white computer paper, as along with a wood pencil, is to write down the calculations. Also, a graph paper can be used to be optimal because the use of the grids, and also because the use of the binary computations, it is needed the use of a binary calculator to minimize errors, and also to convert hexadecimal to binary. The input data is in hexadecimal. A hexadecimal to binary conversion table will be helpful for converting the data more quickly. The output also needs to be in hexadecimal, which the table will be useful for.
To do one round of the SHA-256 hash, we start off with 8 inputs, A, B, C, and D. And the first step is to change the hexadecimal into binary. The first major operation is the majority function. And pretty much what this does is we look at each bit in every position, and if there are more zeros, we put down a 0. If there's more ones, we write down 1 for that position. What this does is it will mix up A, B, and C in a non-linear way, and after the conversion, change that back into hexadecimal. Now for the next step, we look at data A, and we will shift the bits by 2 positions. Now we will shift this 2 more times, this time 13 positions. And now finally by 22 positions. After the shifting is done, now we will combine the 3 data using a function exclusive OR. So if the number 1 is odd, that means that the output is 1. So if the number of 1 is even, the output is 0. We do this for every position of bits, and after that, convert the binary back into hexadecimal. Okay, now the first big chunk is done. Moving on to the next 4 inputs, E, F, G, and H. We do the same operation we did last, converting the hexadecimal into binary, respectively. For this section, we will use the operation, the choice function, and for this we look at data E, and if the bit is 0, we choose the data from G. If the bit is 1, we choose the data from F. And just circle the respective bits and write down the circled bits and convert that back into hexadecimal. once again, we shift the bits, but now looking at the data from E. First, we shift the bits 6 positions, then we will shift it 11 positions, and lastly, we will shift it 25 positions. Combine these data, again, we will perform the binary exclusive OR function to combine the shifted data. And then convert it back into hexadecimal. Now we have more data coming into play. W indicating that the data block is version 2, and K is a constant data that is predetermined by the NSA. Now we write down the H data given, the choice data that we determined for the EFG data, and then we use sum of E, and we perform addition of the hexadecimals. For this part, it'll be easier if you have a hexadecimal calculator. It just saves a whole lot of time. Again, we will do a hexadecimal summation with sum of A. And using the data from the majority function. And then bring down the output that we determined earlier and combine them. Now this will be the new A data we are trying to determine. To find the new B, C, D, it's pretty simple. Just revert back to the data. The new B will be the old A file, the new C will be the old B file, and new D will be the old C. Okay, now the last calculation to find new E, we use old D data, jot that down, bring down the same output that we used on the last calculation, and again, hexadecimal summation. And this output will be the new E. Now we have new E. Like we did last time, the new F, G, and H will just be the old E, F, and G. Okay, simple enough. And this is how you do one round of the SHA-256 hash algorithm by hand.
In order to perform binary addition, you must first learn the addition rules. When adding two zeros, the result is 0 with a 0 carry. When adding 0 and 1, or 1 and 0, the result is 1 with no carry. Adding a binary 1 to 1 results in a 0 with a carry of 1. These rules are represented here visually. in this example, we will add 28 and 43, and we should get a result of 71. First, you must convert these numbers into binary form. If you can't do this on your own, use a binary calculator to help you. Next, starting from the right, add each pair of binary numbers according to the rules described earlier. Finally, convert the result back to decimal C that the answer is indeed 71.
Another important problem you might run into is how to do a binary shift. It's quite simple, but can seem a little confusing at first. So you move every single digit one spot to the left. So in the example I have, the digit in position 0 will move to position 1. So now you have a spot left over at the very end in the new position 0. So you add a 0 to that spot. So now the number will be one digit larger, and we'll have an extra 0 on the beginning of the number.